All right, today we're going to talk about a really cool subject in material science, which are phase diagrams. Doesn't sound cool. Just wait for it. It's going to be cool. All right? So our learning objectives are as following. We're going to figure out what are the variables that dictate the phases that are present. We're going to do this first in a unary phase diagram, meaning one substance, like pure water, for example. We're going to introduce something called Gibbs phase rule, which lets us predict the degrees of freedom. I'll describe what that means. We'll actually be able to sketch the free energy as temperature or pressure changes, what happens to different phases for some basic phases. And if we get time, we'll even introduce eutectic diagrams and talk about solid solubility. I don't know if we'll get that far. Okay, so first off, phase diagrams, what are they? We can think of them as a chart that shows the conditions where distinct thermodynamically, separate phases are in equilibrium. So think of it like a treasure map. If there's one phase that's of particular interest to you, how do you actually get to that phase, right? Or if you have that phase, how do you prevent it from switching to another phase that you don't want, right? These phase diagrams tell you. Now, they only tell you part of the story because there's this key word, thermodynamic, right? The thermodynamic limit of these things. And sometimes thermodynamic equilibrium takes a very long time to reach, right? And so kinetics might have something else to say about these diagrams. But first we'll learn about thermodynamics, and later we'll talk about kinetics, how that might change them. So first off, when I talk about these, great materials, do you have an example? Maybe turn to the person next to you. What am I talking about when I mention why you'd care about phase diagrams? When things change in and out of a phase, why might that matter? Okay. Jare, what do you got? Okay, listen up. Jare's dropping fact bombs on us. All right, Jare, you want to consider what now? Yeah. Absolutely. What else? Hand over there.
I think of like refrigerators or AC systems where you have the refrigerant like condensing and vaporizing and all the different like phases in between where you need to know what pressure and temperature that has to be at.
Yep, absolutely. And there's lots of other examples we could point at. It's been partially debunked, but a lot of people thought that the reason that the Titanic went down, the reason that it sunk, and it sunk as rapidly as it did, is because in the cold North Arctic Ocean, it was so cold that the steel was more brittle than it would have been as they constructed it, as they designed it for, right? And so instead of bending, right, yielding, it actually fractured. That's been partially borne out. But that sort of scenario you can imagine, right? If you heat something up or cool it down or you introduce a corrosive atmosphere, phases will change, right? And so these diagrams tell us how they'll change so we can plan for them appropriately. Here's an activity we can think about. Imagine that you've got two materials, A and B, right? It's a 75 by volume % mixture of A and B. A and B could have totally different properties. A could be, so for example, I think I've got right there, B is a ceramic and A is a metal, right? So think of all the different ways that you could make a 75-25 mix, right? You could have the following. You could have maybe this, right? If you're looking through a microscope at it, what if it looks like this? You've got 25%, B? So you've got 25% ceramic in little globs, and the rest is metal as a matrix, right? Think what the properties would be for that. Now compare that to this one. Maybe you've got thin stripes of the ceramic going all the way through it, right? Like a ceramic metal matrix composite, right? These are going to have very different properties. What if you had, lots of other different examples of ways of arranging these things? What if you had grains, right? So you have grains of your metal, but all along the grain boundaries, and we'll talk about what grains and grain boundaries are soon. But what if your ceramic segregates to the grain boundaries, right? The properties that you'll get out of these things are all totally different. The strength, the electrical conductivity, the thermal properties are totally different. But these are all still a 75-25 mixture of your two materials. So how do you know what microstructure, because that's what these are microstructures, how do you know which one you're going to end up with? Phase diagrams tell us a lot of that information, okay? So let's dive into what is, I apologize, today's you're going to see the best demo of all time. So everything else after today, my apologies, it won't be as good. Okay, what I've got here is, make sure that's turned off. So we've got an iron wire, a piece of iron wire stretched between two posts. And then I've got this big device here called a variac. A variac is just a variable potential source. So it's going to the wall, and it goes between 0% up to 100% if I turn that dial. So if I give it 100%, it's getting 120 volts at whatever the frequency of our walls is at. What, 60 hertz or whatever our walls are at? What does 60 hertz mean? That's 60 times per second, the polarity of that 120 volts is switching. So it's positive 120 volts and 0. Right? And 60 times a second, that's switching. So really quickly, that's how alternating current works. That's what our devices all run on because it's more efficient than DC, right? So what will happen is my question to all of you. What happens as I start to turn this dial, right? I've got, this thing runs to two, positive and negative wires. It connects to this iron wire. On this wire, you've got a magnet hung, and you've got just a weight. So what's going to happen as I start to crank that dial off of 0? The magnet might spin around and do something funky, maybe. What's going to happen? So, we don't know, is the answer. I'm not hearing anything definitive. I'm hearing spinning motion, or seeing spinning motions. So you're all thinking about the magnet. Apart from the magnet, what will happen? I'm going to pass a lot of current through a wire. It's going to heat up. Now, why does it heat up? So as I increase the potential difference across these two wires, I'm creating an electric field. An electric field is just a difference in voltage divided by the separation. What is this, like a meter and a half or something apart? So the 120 volts, or whatever fraction of that I deliver to it, there's going to be an electric field that's constantly switching. So the electric field, if there's any charged particles in an electric field, what do? They get accelerated. They feel an acceleration, a force on them, right, in response to the electric field. So all the electrons that are in this wire are going to be accelerated back and forth at 60 hertz, right? They're going to jostle back and forth in the wire. What's that going to do? It's going to heat it up, right? Because they collide into atoms and they impart a little bit of energy, right? And the more times that they collide into things and the less efficient that process is, the more material will heat up. We'll talk way more about this later on in Chapter 12 with electronic properties. So let's go ahead and do it. I'm going to crank it up to like 20 to start with, 20%. And about, so first off, that happened. So what was that? It wasn't the rust. What was on there was to prevent rust. What do they put on pure iron wire? You don't do it on steel because steel's a little more corrosion resistant. You put oil on it, right? So this is like from Joann's. You're all welcome. I went to Joann's for you. And I got some iron wire that I don't know why they have it at Joann's, but they do, right? And they have it coated in a little bit of oil to block the oxygen from getting it. So remember how we talked about the passivating layer with the aluminum oxide? This is being there instead of the passivating layer because iron doesn't form a passivating layer. Instead, we coat it with a little bit of oil and it protects it, right? So we're at 20% of our 120 volts. Let's increase it. We're going to go up to 30. Now, about half the time we trip a breaker when we do this. That's key. She noticed that because she's right up front, she can see that it's actually drooping. The wire is drooping. Why on earth would it be drooping? It is. It's getting bright red. Why would it be drooping? It's not because it's more ductile. That's a good guess. The end posts are fixed, meaning the total distance from end post to end post isn't changing, but the wire is getting longer, and that's why it's drooping. Why would the wire be getting longer? Yeah, you've heard of this before, thermal expansion. You heat things up, and in general, with a few funky exceptions, they get longer. What you're seeing is thermal expansion. If it's glowing, that means it's around 700 Celsius. So we're seeing a pretty 700 degrees difference. What's going to happen if I keep on doing this? Let's go up to 40. Sometimes this melts and gets really dramatic. We're going to try and avoid that. Okay? Watch the magnet and watch the height. We're at 45, where I start getting a little sketchy. Because I don't want it to melt on me again. Okay. The magnet dropped. A bit funky. We're going to go to 50. Should we go higher? Every time I teach them, like, let's go a little higher. Let's go to 55. All right, we've got a hot spot. Oh, it just melted. I ruined the demo. I got greedy. Bummer. Now we're going to have to watch it on YouTube. So apart from burning the table now, if you watch really carefully, that wire, it droops, and it actually slowed down and stopped drooping. It got shorter. It went up again, and then it drooped a little more. And if I wasn't so greedy, we could have seen it in reverse when I killed the power. Killing the power, it would have gone up. It would have stopped for a minute and gone down suddenly, and then it would have gone back up again. So what is happening? When we talk about thermal expansion, I keep on turning this dial, giving it more power. So why would it ever stop expanding? If I'm heating it up, why did it stop expanding? What do you think is happening? We're talking about phases this chapter. It has to do with phases. Yeah. So what on earth is a phase? If I would have asked you at the beginning of this class, what is a phase? You would have probably said, well, like gas versus a liquid versus a solid. Those are different phases. Turns out that there are like a gazillion different phases in each one of those, right? Solids, there's a gazillion different solids, right? If you look in these databases where these things get assembled, the one that I have, just at room temperature and pressure, there's over like 25,000 different ways of organizing matter, right? So there's really simple ones, right? We could make, like these students right here are organized in a square, right? And that square, I could translate it over, and there's another square of students. I can translate it over. And there's a missing spot. That's called a defect. We'll talk about those next, like in 2 chapters, right? So there's a defect. There's a missing atom. But like this sort of translates to fill all space. But what if I'd arrange these students differently? What if it was like a hexagon, right? That could also be translated. Or we could do all sorts of other funky shapes. So what happens in the iron wire is that at low temperatures, the atoms are in a what's called body-centered cubic arrangement. We'll talk about what that means next chapter, so don't worry about it for now. It's BCC, body-centered cubic. But at high temperature, it has a thermodynamic driving force to become more compressed. The atoms squeeze a little bit closer together. And as they do that, think about what that would do in a whole wire. You've got trillions of atoms in this wire, and they all, around a certain temperature, decide to squeeze a little bit closer together. So that wire which had been expanding, the atoms all decide we're going to switch crystal structure, and it shrinks because they squeeze closer together. And once that transformation is complete, it goes on expanding just like before. And it's reversible. Had we not blown the demo by our greed, I would have seen this actually start to shrink, but then they expand, they go to the more expanded structure, and it expands before it then starts to shrink again. So these phases of matter are pretty slick, and I'll find a video. I'll post it on the announcement on this because we don't have time to watch it now. To explain why these things switch from one phase to another, let's start with the simplest phase diagram we can imagine, and that's water. Well, there's even simpler. Water's actually a little bit funky, but we're going to start with it. When we plot pressure against temperature, what do you know? If you were going to try and draw boundaries where solid, liquid, and gas exist here, you can use your own intuition. When does water turn into ice as a function of temperature? On this x-axis, if you've got like solid ice out here, that should turn into water other way around. Liquid water should turn into ice at low temperatures, right? So probably we've got solid over here somewhere, and maybe liquid right here. And we'll see if that's right or wrong. Okay, if we increase pressure from a liquid, where's gas going to be? Well, if you start out with a solid and you increase pressure, will a solid ever turn into a gas? No, that's not right. What about the other way around? If you decrease pressure, will a solid sublimate and turn into a gas? Yeah, so maybe gas belongs down here, right? Let's write gas and see if we can get this right. So there's some sort of barrier, right? There's a line that if you cross in terms of pressure, and it's going to be as a function of temperature, you'll go from a solid to a gas. Now what about a gas? If you increase pressure, will it turn into a liquid? Can you squeeze on gas and liquefy it? This is how liquefied, gas and nitrogen are produced, right? Liquid nitrogen is just squeezed on air, basically, and then separated. So this must be liquid out here. So you've got solid, liquid, and gas. Now what about the slopes of these lines? This is where it gets a little bit tricky. So water is actually extremely unique. And it's amazing that it is, otherwise life would not exist on this planet. The fact that this line between solid and liquid has a negative slope life would not exist on this planet otherwise, because think what this means. As you go to higher pressure, solid turns into a liquid. What that means is that a solid, ice, is less dense than water, right? Because if you squeeze on it, you can technically convert it to a liquid. If that wasn't the case, ice wouldn't float. Ice floats, and that's why the oceans don't freeze. Otherwise, it would freeze at the surface when it gets cold, sink to the bottom, yield more water, that would freeze. We would have solid oceans if this was the other case. Another material like benzene or many, many other liquids, it's the opposite. This is the exception of the rule that has that negative slope, right? This was one of the reasons why they thought for a long time ice skaters could skate on ice. They said, oh, you've got this tiny little blade and you've got a big fat person on a pair of, ice skates. All that weight is on that thin little blade that's producing a lot of pressure. So on the ice, maybe it's actually converting it to liquid. This is totally not right. They've since proved that not to be the case. But that's what they thought originally, because they knew that existed, right? So this is our phase diagram. What's this point right here? We call it the triple point. What does it mean? Yeah, all three states can exist and the key word is in equilibrium, right? So there exists a single pressure and a single temperature at which this happens, right? So we all live up in the mountains. That's going to be at some relatively low pressure to sea level, right? So if you live in the mountains, let's say that we're right over here, right, Utah. And then we've got our rival, USC, because let's face it, BYU is not a rival anymore. That's a little brother at this point, right? So I've got those backwards. USC is at a higher pressure than us. I got those backwards. So USC is over here. Utah is right there. So what does this mean when you try and boil water, which is this switch between liquid and gas, right? At what temperature will liquid boil at a hotter temperature before converting to gas? Or at which one of these conditions? Utah or USC? Well, the transition, if you start to heat it up, liquid will turn into a gas at Utah at a lower temperature. And at a higher pressure, meaning, sea level, why is USC a higher pressure? Think of the air as an ocean of air. If you're at the bottom of a real ocean, like an ocean of water, you're under a lot of pressure. It's the same thing with air, right? We have an ocean of gas molecules above us. And at sea level, you've got more of it than we do here. And that's why if you're cooking, you'll see all the time in, if it's a good cookbook, they'll tell you how long to boil something for or bake it for, because this line, this temperature that the water's going to be at, depends on where you live, right? That's why you'll notice sometimes if you live for every 1,000 feet of elevation, add 5 minutes or whatever it is, right, to your cooking time, right? Is because we understand, even chefs understand, that phase diagrams are useful, right, and that we need to take into account them, okay? So let's draw some points on here. So point A is our triple point. We've got point B over here. We've got point C right there, and we've got point D over here. Those 4 points are going to be useful to describe something called the Gibbs phase rule. Gibbs phase rule is pretty cool. This is the same Gibbs of Gibbs Free Energy, our first PhD in the United States. He basically came up with this rule. P plus F equals C plus N. What is P, F, C, and N? P is the number of phases, which is in your notes. F is your degrees of freedom. I'll describe what that means in a moment. C is the number of components in your system, right? And N is the number of non-compositional variables, okay? What Gibbs phase rule does is it tells us the degrees of freedom. And what this is useful. It says how many things can we change without changing the equilibrium of our system, meaning the fraction of the phases present. So let's just do an example. Let's pick the triple point that we mentioned earlier. At the triple point, that's point A. I think this is our first clicker question. How many degrees of freedom should be present at point A? Remember, it's P plus F equals C plus N. P is the number of phases. How many phases are present at the triple point? You're going to have 3, because all 3 are in equilibrium. That's the definition of the triple point. So P is 3. F is what we're solving for. C is the number of components in our system. Phases are not components. What it's made up of, those are your components. Now, you might say, oh, water, it's got hydrogen and oxygen, but we're not tailoring that ratio. It's just fixed. So there's just one component here. This is what we call a unary phase diagram, because it's only one component. We're not separating oxygen and hydrogen at any point in this. It's always water. It's just different phases. And then n is the number of non-compositional variables that we can change. What can we change since we're not changing composition? Is there anything that we can change in that phase diagram? We can change pressure and temperature. So there's two of those. So P plus F, 3 plus F, equals 1 plus 2. What is F? Yeah, get your number, get it punched in. Okay, get that in. I'm going to close the poll. Okay, and sure enough, yeah. Always surprising. All right, at points B and C, how will this be different? How many phases of matter do we have? Or what's our degrees of freedom? By the way, what did it mean when we said 0 degrees of freedom at the triple point? That means that we can't change anything and keep that same equilibrium. If you move pressure up and down, you leave the triple point, you'll now not have 3 phases present anymore. If you change temperature, you can't have it. Now, at points B and C, those are both along these tie lines. How many phases are present at points B and C? 2. How many components? It's still 1. And how many non-compositional variables? It's still 2. So now it's 2 plus F equals 2 plus 1. So what is F? 2 plus F equals 2 plus 1. What is F? Okay, I'm going to close the poll, get your answers in. Okay, what do we find? Yeah, there's 1 degree of freedom. What does that mean? It means that we have the option of changing one variable, either temperature or pressure, but if we want to maintain that equilibrium, the system's going to pick the other one. What do I mean? If I'm at point B and I decide for whatever reason that I want to go down in temperature, if I want to maintain that same equilibrium where there's both solid and liquid in equilibrium with one another, the system says, okay, if you're going to do that, pressure has to go up. You can choose one thing, but the system will choose the other. That make sense? We do the same thing with pressure. Okay? Let's go one more. What about at point E? Oh, sorry. Point E is where I'd drawn D before. So it's the one that's in the pure gas phase. If it's in the pure gas region of this, what phases are present? Just 1, just gas. So it's going to be 1 plus F equals 2 plus 1. What is F here? 1 plus F equals 2 plus 1. Get your answers in. One plus F equals 2 plus 1. Closing the poll. Yeah. It's always surprising. So what does that mean? At point D, I called it here, I can choose, I have 2 degrees of freedom. I can go down in pressure or up in pressure, right? I can go left or right, higher or lower in terms of temperature, and I have some finite ability to make that still be gas no matter what my choice is, right? So that's what the Gibbs phase rule is. It tells you things that you can change without modifying the equilibrium in some way. And in a Unary diagram, it's pretty straightforward. It gets more interesting when you have multiple components, okay? All right, so first off, what does the real phase diagram of water look like? I really exaggerated this negative slope, right? It looks like a straight line. It's just barely negative. Water doesn't ice doesn't pop up out of water like a cork. It floats, but it's not like crazy less dense, right? It's just a little bit less dense, right? And then check out what else is happening. In the ice region, all the blue stuff, there's all these different numbers like IC, IH, XI. Turns out there's 11 more? I don't know. There's many, so those are Roman numerals, right? There's tons of different types of ice. Ice that you all assume is just like ice, maybe with a little bit of air pockets in it if you've seen snow and things like that, where it's not fully dense. Even fully dense ice has lots of different what we call polytypes, right, or polymorphs. There's lots of different ways of arranging these molecules, right? The H and the C, I think this stands for hexagonal. You put them together in a hexagonal arrangement as opposed to, I think C is probably cubic, right? There's lots of different ways of arranging ice. Now, where would this phase diagram come from? Somebody measured this. We have it. Where did it come from? If you wanted to recreate this, what would you do? Apocalypse comes. All of our knowledge is lost. You're starting over. You need to recreate this phase diagram. What do? Yeah, you could experimentally, what you said was fix it at various pressures, right? Try and take some sort of device that fixes it under a pressure. Easier said than done. And then heat it up and see where you switch from one phase to another, right? And this in the old days is how they did it. They did experimental observations under, most of the time, right here at 1 atmosphere. Where's 1 atmosphere? Right here, right? 1 atmosphere, because that's the easiest, right? Controlling pressure is hard. Heating things up is easy, but we can see when they switch from different phases to one another, right? There's a better way to do this, right? Experimentally measuring them, especially at crazy high temperatures or crazy high pressures, gets really hard. Fortunately, you all are now masters of Gibbs Free Energy, right? A room full of masters. Yeah, question?
I was just wondering this while I was doing the reading. How do you maintain pressure?
How do you maintain pressure? So let's say that you're generating, so if you want to maintain it at 1 atmosphere, but you've got a reaction that's producing gas, you'd have to have a permeable confinement, right? The reaction it can't take place in a steel vessel that's sealed up. You'd have to have a vessel that can expand, basically. Now, because expanding, that violates some of our assumptions about work being done on the system. So enthalpy versus Gibbs Free Energy become like maybe one is better than the other under those scenarios. We don't need to worry about it in this class, but it's a great question. You'd have to have a flexible, basically, surrounding. In that way, it's still under atmospheric pressure, but you've given it the ability to expand. Otherwise, ideal gas law says PV equals nRT. If you increase the number of moles, right, something's got to give. Either pressure's got to grow up or it's got to expand. All right, we're going to use free energy, and we can recreate this phase diagram, okay? We're going to do that by sketching 2 things, okay? So we're going to sketch free energy as a function of temperature. So let's draw some axes. Here we're going to plot the Gibbs free energy as a function of temperature. So as you change Gibbs free energy, we're going to sketch some things. And then we're going to do the same thing over here, but as a function of pressure. Gibbs free energy versus temperature or pressure. So let's go back to this diagram, and let's pick the ambient pressure where we all live as human beings, right? And what happens as you go across increasing temperature? What happens as you increase temperature? You go from solid to liquid to gas. And there are points right here and right here in terms of temperature where you transition from solid to liquid to gas, right? So what we're going to do is we're going to draw those on this x-axis. We're going to say that there's a point where you go from solid to liquid to gas, okay? Now we can do the same thing with pressure. Let's pick room pressure, or room temperature and change pressure. So room temperature is right here. Where is it? Sorry, it's right here. So as we go up, is that going to disappear? I don't know what's doing that. You start from vapor, though. If you're right here, you're going to start as a vapor and turn into a liquid, okay? If you start out just to the left of that triple point, you'd go from vapor to solid to liquid. So it's going to change. The order is going to change. Well, let's assume that we're at room temperature for a minute. So it's going to go from vapor to liquid to solid, okay? So we're going to go vapor to liquid to solid as you increase pressure, okay? So we're going to draw this. We're going to say gas, liquid, solid, okay? Now, we're going to be able to draw some lines that represent our different phases. So let me change colors and do this. We're going to say that this is our color for solid. We're going to do a different color for liquid and gas. Let's say this is gas, purple, and we'll do blue for liquid. Okay? So we're going to draw lines. Now, last chapter we talked about free energy. What reaction will happen? Does energy want to be increased or lowered? For it to be spontaneous, we want to go down in energy. If you have the option to be in a higher state and you can go lower, it's going to switch to the lower state. So we could draw lines that represent the free energy for all these phases, and we're going to see that the one that has the lowest free energy is the one that's stable. Okay? And then we learned one other thing. If you remember from last chapter, we said that H equals U plus PV, right? Let me get the rest of my notes. What did G equaled H minus TS, and we said because of that the derivative dg dt, if you take this partial derivative, that's sloppy. Let me do it down below, so I'm out of space. But dg dt, if you take the derivative of this expression up here, dg dt, it should be negative entropy. Free energy should scale as negative entropy. Okay? Negative entropy. Meanwhile, over here, dg dp scaled as the positive volume. Or in other words, we're plotting here free energy versus pressure. So the derivative should be the slope, right? The slope of that line for these different phases should be proportional to volume. And over here, the slope of this line, dg versus dt, should be proportional, we're going to be a negative line, and it's going to be proportional to the entropy. Or in other words, the line that has the steepest slope should be the one that has the highest entropy. You guys follow? So let me ask you this. Solid, liquid, gas, which one has the most entropy? Gas definitely has the most entropy. So we're going to draw a negative line because it's negative S, and we're going to draw it with a really steep slope. So let's draw it like that. Okay? That's our negative line with high slope because it has a high entropy. Now, between a solid and a liquid, which one has more entropy? Solid versus liquid. Solid, every atom is sort of in its place and they can vibrate a little bit. Liquid, they're moving all over the place. Way more entropy in a liquid. So it's got not a higher slope than that one. Let's draw it like this. Notice where I'm choosing to make those two intersect. I cause them to intersect right at this point. Or in other words, if you are, let's say you're right here. You're a liquid at this high temperatures. If you're at that point, you can choose to lower your energy by going down and turning into a gas. That's why liquids turn into gas at this higher temperature. Y'all follow? Are there questions on this so far? Now, a solid is even less entropy than a liquid or a gas. So when we draw its line in green, it's going to be it's still negative sloped, but it's even less of a slope. So maybe like that. So the same thing as before. If you are let's say you're a liquid now, but you're a liquid at this temperature, you can lower your free energy by going down and turning into a solid. This is pretty slick. Yeah.
Ideal graph, should the purple and green also intersect on that line?
Should the purple? No.
Okay.
We'll talk about that in a minute. So if literally to figure out what phase is present, you just look at the line that's the lowest down. The one that's the lowest free energy is going to be the one that's favorable. For this first region, the green line is the lowest, so you've got solid. Over here, the blue line is the lowest, so you got liquid. Over here, it's purple, so you got gas. Everybody see this? Or in other words, if you could come up with really good calculations of how free energy changes as a function of temperature, pressure, composition, you can plot these little spaghetti lines and just look for the lowest phase. And that is how you can make these really complicated phase diagrams, right? It turns out you can measure a few thermodynamic properties, and from those, you can come up with expressions for all of these different phases and then figure out where they ought to exist from a thermodynamic standpoint. And then all you have to do is test a few points and make sure that it actually matches. If it doesn't match, maybe there's a problem with one of your calculations, but that's the typical way that you can generate these things. Are there questions so far in this first one? Do you see that again? As you increase temperature, removing this way, you go solid, liquid, gas, and that's what we see is solid, liquid, gas along that line. Now we're going to do something else over here. Okay, at room temperature, we said that we go gas, liquid, solid. Okay? This time when you do it as a function of pressure, the lines we draw are going to be positive lines, and they're going to be proportional to the volume. So, if it's water, what has the most volume on a per mole basis? Solid, liquid, or gas? Definitely gas. So we're going to start out with a really positive slope. High slope, positive. Okay? Now, our next one, which one has more volume? Liquid or a solid? We just said that a solid has a higher volume. That's why ice floats. If it had a lower volume, it would be more dense, it would sink. So the next highest line needs to be solid. Make sure I get this right. Okay? I'm going to draw it like that. Oh, I've jacked this one up. We should have done it before. That's all right. So this is equally interesting. Okay, and then liquid is going to be the lowest volume, so it's going to be the lowest positive slope. We're going to have to modify our liquid line in a minute, our solid line in a minute. Liquid's going to look like this. It's going to be the lowest volume, so it's the lowest slope. So from this diagram, it looks like you go from gas to liquid, and you should never turn into a solid, right? Fair enough? It looks like you should never turn into a solid. So what's wrong with this? What do you think we need to do to modify this? If you switch solid and liquid, it won't work because you turn into a solid first and then a liquid, which is what you see if you're just to the left of the triple point. Again, if you're just to the left of the triple point, you go gas, solid, and then eventually, since this is actually tilted, you turn into a liquid. So that would be to the left of the triple point, you had the right idea. To the right of the triple point, what do we need to do to this drawing to make it actually work? It's a bit of a trick. We've been using one line to represent solids, but there's 11 different types of solids. They should all technically have their own line. They should all have their own line, right? So while that green line might represent the ice that we know and love, hexagonal ice, which is for the vast majority of instances where we interact with in nature, this is the solid we interact with. The ice up there, what, number 11 or 7, whatever that is, that one would need its own line, okay? So we would need to introduce a new color, and it would need to intersect this in some way, right, at that point. Are there any questions on this, on how these relate with entropy or volume? What if I had you draw it? Let's actually do this. How much time do we have? Yeah, why don't you turn to your neighbor and sketch what this thing might look like at the triple point. Draw dg dt and draw dg dp at the triple point. Okay, dg dt, is that our first one? Yeah, dg dt. So at the triple point, we're going to be right here. At low temperatures, you'd expect to see pure solid. You hit that point for one brief second, liquid is now also favorable. They're all equally favorable, and then it switches to vapor. So what does this look like? So let's draw it. There's going to be one point where this happens, one temperature. We're going to have a really high negative slope for our gas. We're going to have a less negative slope for our liquid. I kind of botched it. And then we're going to have an even less negative slope for our solid. That's crappy. Let me try that one more time. Right? You guys see that? At one point, so as you increase from low temperature to high temperature, it's a solid, because that green line is a solid, all the way up to this point where all of a sudden all three of those are equally favorable. That's why they're in equilibrium with one another. And as soon as you heat it up a little bit more, you get pure gas, right? So a very common homework or midterm type question is to give you a phase diagram for water and pick a temperature or a pressure and say, all right, sketch the lines for this thing that you would use to recreate this phase diagram. Let's do it one more time, but let's do pressure now. We're going to do dg dp. So we're going to change pressure at the critical point. So right here, we're going to go up and we're going to change pressure. Low pressure versus high pressure. At the triple point, you're going to start out as a vapor. You're going to have a brief moment where all phases are in equilibrium. And then you're going to turn into a liquid. Right? So let's sketch that. And remember, the slopes have to correspond to what we know about these things. So you're going to have this. There's one point at which it's going to have its triple point where all of them are equally favorable. We have our liquid, which is our next, solid is our next largest volume, excuse me. Solid is less dense than liquid. So draw it right there to intersect. And then we're going to draw our liquid, which is the lowest volume, so it has the lowest slope right there. So in this one, we go from a gas into a liquid. Is that right? At that point, we go from a gas, we touch solid for just a moment, and then we turn into a liquid. Any questions on this? No? Yep. Okay. So first off, we've been making some assumptions. Like, for example, we've just been drawing one solid line, but we know that there's 11 different types of solids or whatever there is, so that's a problem. We should be including all those lines. And since we're never accessing them in these temperature regions, where would they be on these plots? Since you never see them in these temperatures and pressures, they must be way up there. And they exist, but they're way up higher, so they're never the thermodynamically stable phase. Or in other words, if you did put ice in one of those wacky phases at crazy high pressure, it would much rather drop down to whatever the lowest line is. And so it will spontaneously switch from one phase to another. Just like our wire spontaneously switched from one phase to another when we changed the temperature. Okay? Another assumption is that we've been dealing with straight lines, modeling these things as straight lines, and that is not always acceptable. Sometimes they curve and things like that. Right? This is just an approximation. Right? When we said dG/dt equals negative entropy, what if the entropy of the system changes as a function of temperature? We have to account for that, and that's going to change the slope of these lines. They'll stop being linear. They'll start being curves. And then lastly is we've been talking about a unary non-multi-component system. As you start to change the number of components in a system, let's say you remove some water and you add some salt or something, then these curves start to behave really weird. There's a derivation at the bottom of the notes. You can check it out. It's beyond the scope of this class, so don't worry about drawing those things. But I'll just realize that you can draw like parabolas. You can draw kind of McDonald's arches. It gives all sorts of funky shapes, which leads to far more complicated phase diagrams than this. Okay? We're out of time, so we'll pick up here next time, and we'll start introducing more than one component.